of -1. Okay, so if I consider this x and y as a number, that this z becomes complex number. If I consider x and y as variables, then this z becomes complex variable. Okay, so basically what we have here, z is a function of x and y. Okay, z is going to be the function of x and y. And now we are going to consider the function of this function again. Okay, so we'll be having the function of complex variable z is denoted as w is equal to f of z, okay, or simply f of z. There will be having, this is going to be u plus I, okay, where u is again a function of xy and v is also the function of x and y. So u is a function of xy and v is again a function of x and y. Now we will see how this structure we get. Okay, so this u, as this x is the real part of z, y is the imaginary part of z, the same is followed in the function. So u is a real part of this f of z, v is a imaginary part of this f of z. So let us try with one function and let us see how this u is going to be the function of xy and v is going to be the function of xy. Okay, so we consider a simple function f of z is equal to z square. Now what is z here? X plus iy. So if I put x plus iy here and take the square, now what we do is we consider the square. So how we know a plus b bracket square is equal to a square plus b square plus 2ab, or we write a square plus 2ab plus b square. Okay, anyway, so this is the formula for a plus b bracket square. Now using this formula, let us expand this. So this is going to be a and this is going to be b. Okay, so using this, if we expand, then what we get here, f of z is equal to, so it will be x square plus iy square plus 2x and this is iy. Okay, now simplify, so it is x square plus I square and y square plus 2ixy. So what we know about this I, so I square is equal to minus 1. So I square is going to be minus 1. Okay, and hence what we have here, so this term becomes x square, this is minus 1, so it becomes minus y square, and you have here 2ixy. So this is false, but simply f of z I can write as the term without I and the term with I. So x square minus y square and plus I, this is 2xy. So I can write this as u. So we have here, this is f of z, and so this is f of z, and I consider this as u plus iv. So where you will be having u is going to be x square minus y square and v is going to be 2x. So you can see now that the function u is a function of x and y, and the function v will be the again a function of x and y. So that's what we have claimed, that u is going to be the function of xy and v is also going to be the function of xy. And once we have this u, the real part, v, the imaginary part of the function, then we have the function of complex variable z. So as this variable is complex, its function is going to be complex. Okay, so u plus I. One thing you need to remember, that every real is a complex. Okay, so sometimes we get reals also. Okay. So every real contained in. Okay, so we can claim that everything is going to be complex because no real is contained in complex, so everything is going to be complex. Now we need to understand the basic concept, okay, about complex variable. F of z is a function of complex variable. Now, what we know about the limit of the real variable. So for the real variable case, we know that limit x tends to a minus f of x is equal to limit x tends to a plus f of x, and if these two limits are going to be same, then we say that is going to be limit x tends to a f of x. So this is called the left limit and the right limit. So we have here we have a, okay, so x is approaching from left and x is approaching from right. Okay, so if this left limit and this right limit is the same, then we say this is going to be the limit of the function. So this is in the real case. Now we replace this variable x by the complex variable z. But when we consider the complex variable z, so z has x plus iy. So we have to consider x as well as we have to consider y. Okay. Now, hence, if I consider this as a neighborhood, okay, suppose I consider a small number epsilon. So what this will be? This will be a minus epsilon and this will be a plus epsilon. Okay, so here we can say that whenever x is in the neighborhood of this a, precisely the epsilon neighborhood of a, then this value is in the neighborhood of some constant value L, which we call as the limit of this function. Okay. And that's why when we define the limit of this function f of z, then when z is in the neighborhood of some point, then the limit of this f of z will be in the neighborhood of some constant. And that neighborhood for f of z, if we consider epsilon, then here we can consider delta, the another positive number, or here we consider epsilon, then we can consider here delta. So this is also called as the epsilon delta definition of limit. Okay, so I will choose two positive number, one for the neighborhood of this f of z, another for the neighborhood of this z0. So this is the real case. Now we define the complex case. So what will be having? Let f of z be the function of x variable z, and then the point or the constant L is said to be limit of f of z as z tends to z0, another complex number. If so we can now there exists a pair epsilon and delta. Okay, so we write it properly. Okay, there exists a pair epsilon and delta. So if for every epsilon greater than 0, there exists a positive, precisely small positive number delta greater than 0, such that whenever f of z is in the neighborhood of L, precisely the epsilon neighborhood of L, okay, for all z in the neighborhood of z0, and this is precisely the delta neighborhood. Okay, so if z is in the delta neighborhood of z0, then f of z is in the epsilon neighborhood of z0, and this simply we write as limit z tends to z0, f of z is equal to L. Okay, so this way we can define the limit of the function. Okay, once we know limit of f of z, then similarly we can define the continuity. Okay, so the continuity of f of z. Okay, so what we have as a continuity, so the function f z of complex variable is said to be continuous at z is equal to z0 if for every epsilon greater than 0, there exists a small number delta greater than 0 such that this f of z is in the neighborhood of f of z0, besides the epsilon neighborhood. Whenever the z is in the neighborhood of z0, precisely delta neighborhood. Okay, so here we can write this as, that is, limit z tends to z0, yes, f of z is equal to f at z0. Yeah, are you able to see this? Hello?
Yes, sir.
Yeah. I hope you are clearly able to. Yeah. Okay. Thank you. So we can have the continuity. What is the difference in the limit and continuity? Please remember, this limit is a fixed point and continuity is a value of the function at that point where this z is going. Okay. Now, once we have this continuity, then we can have the next derivative. Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Okay. Okay. So in this Jamboard is problem. So then we can define the continuity. Okay. Continuity we got, limit we got. Now we have to define the differentiability. Okay. So we can go for derivative. Okay. So derivative of precisely f of z. Are you able to see this?
Yes, sir. Yes, sir.
Okay. Because some Jamboard is trying to connect. So till that we can continue. Okay. So the derivative of f of z. So what we can have is, suppose that f of z be the function of x variable z. Okay. Then the function f of z is said to be differentiable at z is equal to z0 if limit z tends to z0, f of z minus f at z0 or z minus z0 exists. Okay, so if this limit exists, then we say the function is going to be differentiable, okay, at this point z0. Now, what is the benefit of knowing that this function is differentiable. Okay, so we can define the analytic function. So we define analytic function. Okay, so if we know that the function is differentiable at particular point, so if we consider the particular point z is equal to z0, okay, then we need to see that whether the function is differentiable at every point or not. Okay, so let us see the function f of z is said to be analytic if it is differentiable at every point in the neighborhood of z0. Okay, so when we consider if the function is said to be analytic if it is differentiable at every point in the neighborhood of z0 in the bounded region R or in complex domain it is okay. So either we have a bounded region here. Okay, so we can have any bounded region and any point we consider z0. So if the function is differentiable at every point in the neighborhood of z0 and in this bounded region, this z0 can be anywhere. Yeah, so basically if this is differentiable at every point in the neighborhood of or in this bounded region R, then we say this function is in this region. So it may be the region or it may be the can be guaranteed that the function will be always analytic or can be guaranteed that the function will not be analytic. So what we can have is we need to understand the necessary but sufficient conditions. Okay, so what we have here, we'll see what are the necessary and sufficient conditions for the function to be analytic. Now, if I consider the function f of z, again, so we can have that f of z is equal to u plus iv be the function of x variable. Okay, and then the necessary and sufficient conditions for a function f of z to be analytic are. Okay, so here we need to consider the condition for function to be analytic. Okay, so what are the conditions? So there are two conditions basically that we need to understand. Okay, so what are those two conditions? So first, w by x is equal to w by y and w by x is equal to minus. So here we need to understand w by y. Okay. So Dabba u by dabba y is equal to minus dabba v by dabba x. So these equations, again, these equations are Cauchy-Riemann equations. These are known as Cauchy-Riemann equations, or simply we can say CR equations also. Okay, then what is the next condition? And we have the next condition. What is the next condition? See, these two equations are necessary but not sufficient. So there may be the function which will satisfy the Cauchy-Riemann equation but may not be analytic. So here these conditions are necessary but not sufficient. Then what is the next condition required? The next condition required is dabba u by dabba x, dabba u by dabba y, dabba v by dabba x, and dabba v by dabba y. Okay, these are continuous. Okay, so these are going to be continuous. So if this happens that the derivatives, first order partial derivatives, satisfy CR equation and then they satisfy this continuity. Okay, so first what we have to do is, if I want to have a function to be analytic, then what we have to consider the necessary and sufficient condition. So by definition, we know that the function is analytic if it is differentiable at every point in the bounded region. Okay, but if it is differentiable at every point in the region, then we don't know how many points are there in the region and at how many points we have to consider. So that's why better to use the necessary and sufficient condition for a function, or to test the function whether it is going to be analytic or not. Okay, and here what we do is we consider the first order derivatives and see that whether they satisfy CR equations or not. And now we consider the continuity of these derivatives. Okay, now we need to understand, okay, whether or how we are going to test the continuity. Okay, so now what we know simply, what are the functions that are continuous? Okay, so we know basically u into v rule for the integration, and we have seen these functions already. So what will be having? We have slide. Okay, so what we know about this slide? So basically this is exponential. So we know this function is going to be continuous. Then we know this is trigonometric. We know this function is going to be continuous. Then we have algebraic, or this is also called as polynomial. We know this is going to be continuous. Then we have inverse trigonometric, and we know these functions are also continuous. Okay, now what we have to do is we have to consider about this L. So what is L is going to be? So this L is, what is that?
Laplace. Laplace, sir.
No, this is not Laplace.
Logarithmic.
Logarithmic.
Okay, so
Logarithmic.
yes, this function, exponential function is continuous, trigonometric function is continuous, algebraic or polynomial is continuous, inverse trigonometric is continuous, logarithmic is continuous. If there are so many functions continuous, then where this condition will fail? Okay, so you are not supposed to show that the functions are continuous or discontinuous, but you are supposed to identify directly that whether they are continuous or not. So if these all are going to be continuous, then what is not continuous, or what is the function which is not continuous? And then there is only one thing that you need to understand. Okay, where it is not going to be continuous. Okay, so if I have all these functions continuous, then we need to know where it is not going to be continuous. Okay, so the point function is not continuous. Okay, so point function is not continuous. What it means? Not. Okay, so what happens if you have this all the derivatives equal to 0? Okay, so suppose you have w by w x, w by w y, and w by w z are going to be 0. So suppose w by w x is equal to 0, w by w y is equal to 0, v by w x. Okay, so we have w by w x is going to be 0, w by w y is going to be 0. Now you can see that this satisfies your equation. Okay, so all these equations are satisfied. W by w x is equal to w by w y, and w by w y is equal to minus w by w x. So if this condition is satisfied, then the CR equation is satisfied. Okay, but can you test the continuity of this? We cannot claim the continuity of these functions. Okay, so if these are going to be 0, then we cannot claim the continuity, and that's why here we can neither say that they are continuous nor say that they are not continuous. Okay, so we cannot judge this simply, and so we put them in the category that not continuous. We don't know continuity, so they are not continuous. Okay, and that's why if this situation occurs that w by w x is equal to 0, w by w y is equal to 0, w by w x is equal to 0, and w by w y is equal to 0, they satisfy CR equations, but do not satisfy or the second condition, or we cannot claim that they are continuous or not. Okay, and that's why we can just simply put that they are not continuous. Okay, now once we can understand, or once we got idea about the derivative, continuity, analytic function, necessary and sufficient data. Okay, then we can try some example based on this. So let us have an example, okay, to understand whether the function is going to be continuous, how we can find the derivative of the function. Okay, so we have again, so this is going to be one. Second, so if the function is analytic, then by using this CR equations, we are able to write the derivative of the function in different ways. Okay, and hence what we know is, so we can say that f dash of z is equal to, okay, so we can say ux plus ivx. Okay, so ux is the notation for w by wx, vx is the notation for w by wx with respect to x. Okay, and then you know ux is going to be vy. Okay, so we can write this as vy, okay, vy times plus ivx. Again, what will be having vy? Vy is w by wy. So we can write this as ux minus iuy. And we can write this as ux minus iuy. This is uy here. So it is going to be uy is equal to w by wy. Okay, and as we know, vx is equal to minus uy, or uy is equal to minus vx. So you can write this function f dash of z in different ways. So if I know u and b both, then I can write it like this. If I know only b, then I can write like this. If I know only u, then I can write like this. Okay, so if I know the real part, then I can write f dash of z like this. If I know the imaginary part, then I can write f dash of z like this. Okay, now we will try whether the function is analytic or not, and if it is analytic, how to find its derivative. Okay, so let us try an example. Okay, now we'll go with the example. So, for example, show that f of z is equal to z square is analytic, and hence find its derivative in terms of z. Okay, so we want this derivative in terms of z. Okay, so let us try to get this in terms of z. Okay, so what we have here, first we need to understand what is going to be u and what is going to be v, and then we will able to say that whether this is analytic or not. So we go with the solution. What we'll be having here, let f of z is equal to z square. Now I want to know what is going to be u and v, so that I can test this function satisfies here equation and is the first order derivatives are continuous or not. Then only I can say this is going to be analytic. So what we do here next, we put z is equal to x plus iy. Okay, and hence what we'll be having, f of z is equal to x plus iy bracket square. So this we know, x minus y square, and plus we have 2ixy. So we got here f of z is equal to x square minus y square plus I and 2xy. So this is going to be the real part and this is going to be the imaginary part. So I can claim that f of z is equal to u plus iv, and where I'll be having u is equal to x square minus y square and v is equal to 2xy. Okay, so now if I got u and v, okay, so got u and v, and now what we have to do is we have to test these conditions. Okay, so now this symbol is for the partial derivative. So when we find the derivative with respect to x, we treat y as a constant. Okay, so let us try to find the derivatives of this u and v. Okay, so what we'll do is we consider the derivative of u by dabba x. Now I am finding with respect to x, so that means y is treated as a constant and the derivative of y will be 0 here in this case. So derivative w by dabba x is going to be the derivative of x square only, and that is going to be 2x. Now w by dabba y. So when we are finding the derivative with respect to y, this x is treated as a constant and the derivative of this term is going to be 0. Okay. So now what is the derivative of this u with respect to y? So the derivative of this term is going to be 0. The derivative of this y square is going to be 2y and this minus sign here. Okay, so we get the derivative to be minus of 2y. Okay, so we got here this is going to be minus of 2y, and we consider about this v. Okay, so what we want derivative of v with respect to x and derivative of v with respect to y. So derivative of v with respect to x. So when we consider the derivative of v with respect to x, we consider remaining terms to be constant. So 2y is going to be constant and the derivative of x is going to be 1, and dabba v by dabba y. So when we consider the derivative with respect to y, we treat x as a constant. So we will be having here this is 2x, and the derivative of this y is going to be 1. So here we got the derivative of this u and v with respect to x and y. Okay, now once we have this derivative with respect to u and v, the derivative of u and v with respect to x and y, then what we have here, see, Now, can we have the derivative of u with respect to x and double v by double y? So it's going to be same. So what we can have is double u by double x is same as double v by double y. Now you can see the derivative of this u with respect to y is this term, and then derivative of v with respect to x. So can we write this as double u by double y, and so we can say double u by double y is equal to minus times, this is going to be minus times double v by double x. So what we can say is that is the Cauchy-Riemann equations are satisfied. So here we can say the Cauchy-Riemann equations are satisfied. So when we have the Cauchy-Riemann equation are satisfied, then we need to test the next condition. So what is the next condition? Next condition is that this derivative must be continuous. So test the continuity of this derivative. So what do you find? Are they continuous? What do you find? Are they continuous?
Yes, sir.
So here if you see
Yes, sir.
this double u by double x is 2x, double u by double y is 2y, double v by double x is 2y, and double u by double y is going to be 2x. So all these are algebraic functions, all these are polynomial functions. Okay, so we can say we know that the polynomial functions are going to be continuous. So obviously if I consider this y is equal to 2x, then it is a line which is continuous. If I consider this x is equal to minus 2y, it is a line which is continuous. So that's why these all functions are going to be continuous. You are not supposed to prove they are continuous. You are supposed to identify that they are continuous. Okay, and hence here you can say that yes, these are going to be continuous. So we claim here, okay, since double u by double x, double u by double y, double v by double x, and double v by double y are continuous. They are continuous. Okay, so once you know that they satisfy CR equation and then they are going to be continuous. Okay, so what you can say, by necessary and sufficient condition, this function is going to be analytic. Okay, and if it is analytic, then we are able to find out its derivative. Okay, so we have already calculated the first order derivative of this f of z, u and v. So using this u and v, we are able to calculate f dash of z. So what we can say is, by necessary and sufficient conditions, f of z is analytic. Okay, so this is going to be analytic function, and hence we have, so what we are having, f dash of z is equal to ux plus ivx. Okay, so what is the value of ux we have here? So we can see ux is equal to 2x, and vx we want, so that is going to be 2y. So what I can write this as is going to be 2x plus I times 2y. So 2 I can take common, and I'll be having x plus iy. But what is this x plus iy? It's going to be z. So I can say that this f dash of z is equal to 2z. Okay, so this is the another way to find the derivative of the function. So here we got f dash of z equal to 2z. And what we know usually, so we know that the derivative of x square, what do we know the derivative of x square? So derivative of x square is 2x, and that's why here we got the derivative of z square is going to be 2z. Okay, so that means all the rules that we have seen for the derivative, okay, are applicable in the complex plane as they are. Yeah.
Estamos number one.
Okay, so here, what Okay. So here, what we know is the rules of derivative that you have seen in diploma are as applicable in the complex domain also. Okay, so there is no doubt that whatever the rules we have for the reals are applicable for the complex. Okay, the only thing is that with some modification and with some conditions. Okay, so now once you have understood the analytic function, okay, then we need to understand the next concept. We have harmonic function. Okay, so here we have seen the first order derivative of f of z. Okay, and first order derivatives of this u and v. Now, what if I consider the second order derivative, and if I know that there is some relation between this second order derivative, okay, and this terms, okay, then what is the relation, and what I can comment on that relation. So we know that u is a function of x and y. Okay, so what we know about u, we have seen that it is going to be the function of x and y. So what we have here, the function u of xy, function u of xy is said to be harmonic function if we have here double square u by double x square plus double square u by double y square is equal to 0. So we know u is going to be the function of xy, and now here if I consider the second order derivatives of u with respect to x and the second order derivative of u with respect to y, and if these two second order derivatives satisfy this condition, then we say this is going to be the harmonic function. Now question is how the harmonic function and analytic function are related to each other. Okay, so here harmonic function and the analytic function are related as, so if I have the function f of z, okay, so suppose I have a function f of z, like f of z is equal to u plus iv, be an analytic function. Okay, then what will be having u and v, okay, both are harmonic functions. Okay, these both are harmonic functions. Okay, that means u also satisfy this equation and v also satisfy this equation. So that is double square u by double x square plus double square u by double y square is equal to 0, and double square v by double x square plus double square v by double y square is also equal to 0. Okay, and now when this u and v are the real and imaginary part of this analytic function f of z, then they are called as harmonic conjugate of each other. So what we have here, they are called as harmonic conjugate of each other. So if f of z is equal to 2 plus iv is analytic function, then u and v are called harmonic. Okay. Now once we know this one, then as I have given you the f of z in terms of the derivative f dash of z in terms of ux and vx. So if we know only function u, or if we know only function v, then how we are able to calculate the f of z. So here, if I know f dash of z is equal to ux minus ivx vy, then here if we know f dash of z is equal to ux minus iuy, or if I know f dash of z is equal to vy plus ivx, then using these two equations, if I integrate these two equations, I am able to get f dash of z. So if we know real or imaginary part, then we are able to get the original analytic function f of z. Now, how we are able to get this analytic function f of z? If we know the real or imaginary part, then there is a method called Milne-Thomson method, which helps us to get the analytic function when we know the real or imaginary part. So next, we need to understand the Milne-Thomson method to get the analytic function. So here we have Milne-Thomson method. Okay, so this method can be used when we have the real or imaginary part, or even the combination of real and imaginary part. Okay, so first we'll consider when the real part is given. So if the real part u is given. Okay, so suppose the real part is given. Now we have 4 steps to get the analytic function using Milne-Thomson method. So what is the first step? So first step is assume that let f of z is equal to u plus iv be an analytic function with real part u of xy, because u is a function of x and y. Okay. Now the second step. Okay. So what we have to do is, we know only u, so we have to find out ux and uy. Okay. So what we'll do is consider dabba u by dabba x. Okay. And name this as phi1 of xy. Then we will find the another derivative. So this is going to be phi2 of xy. So phi2 of xy is equal to dabba u by dabba y. Now, once we know the first order partial derivative of u with respect to x and the first order partial derivative of u with respect to y, okay, then the third step. What we have to do in third step, put let it equation 1 and let it equation 2. So put x is equal to z and y is equal to 0 in equation 1 and 2. Okay, so once you put this x is equal to z and y is equal to 0 in equation 1 and 2, then we get, so what we are able to get here, see, we'll get phi1 of z0 and we get phi2 of z0, because we are putting this x is equal to z and y is equal to 0. So we'll get phi1 of z0 and phi2 of z0. And fourth and important step, or the last step, we have then by Milne-Thomson method. So we'll be having here by Milne-Thomson method. Okay, so please do not abbreviate, write it in full. By Milne-Thomson method, the analytic function f of z is given as. So we have to integrate. That means f of z will be, on this side we have f dash of z, so it will be integrated as f of z, and this side will be integrated. So ux, what we have considered ux, it is going to be phi1 of z0 with respect to dz minus I, and is going to be uy. So it is going to be y2 of z0 dz. But when you integrate without the limits, you have to add the constant of integration, that is going to be c. Okay, so this is how we can find the analytic function by Milne-Thomson method when the real part is given. So similar way we can use when the imaginary part is given, but while treating v, we have to take care that we want Ey plus Ivx. Okay, so that we need to see here. Okay, what do we want? When the imaginary part v is known, then it is going to be Vy plus Ivx. Okay, so if I want to have Vy plus Ivx, then I have to change the notation for first derivative and for the second derivative. So let us see what we get here. Okay, so the second type, if we know if the imaginary part E is given. Okay, so very similar steps we have to follow. Only thing is that the calculation we have to do with respect to B now. Okay, and hence what will be having the first step, always declare the function. So let f of z is equal to u plus iv. Okay, be the analytic function. Okay, this has to be analytic function with imaginary part. E is equal to v of xy. Okay, now second, what will be having? Consider the first order derivative, but now we want vy first. So the derivative of v with respect to y, and let's name it psi 1 of xy. So this is equation 1, and what you'll be having, the next derivative psi 2 of xy is equal to gamma v by gamma x. Okay, so let this equation. Now the next step, which is common because we are using the same method. So this is the step of the method. That's what we have to do. Put x is equal to z and y is equal to 0 in equations 1 and 2. Okay, so we get here, we get psi 1 of z0 and we get psi 2 of z0. Okay, so once you get psi 1 of z0 and psi 2 of z0, then you can write the next step by Milne-Thomson method. Okay, the analytic function f of z is given as, or given by, f of z is equal to, we have integrated this, so we need to integrate this as vy. So it is psi 1 of z0 dz plus I vx. So it is going to be psi 2 of z0 dz and the constant of integration c. Okay, so this way we are able to get the analytic function by using the Milne-Thomson method. Okay, now we will try to solve some examples which may be asked in the examination as. Okay, so here we'll consider the examples. So what you'll be having, so simple, if it is a MCQ question, okay, then what we'll be having, find the analytic function corresponding to real part x square minus y square. Okay, so the option A is w plus c. Okay, so here w is going to be the function. Okay, right here. So I can say w is going to be the function. So w is equal to z plus c. The option B is W is equal to Z square plus C. Option C is W is equal to Z square plus Z plus C. And D, the option is W is equal to 2Z plus C. Okay, so these are the different options that are given, and then we want to find out what is the analytic function corresponding to this real part. Okay, so by looking at this, you can directly say which is going to be the real part, or you can solve easily and then get the real part. Okay, so here we will see how to solve this and how to get the real part, the analytic function. So we go with the solution. Okay, so what we have here, like f of z is equal to u plus iv. I am using the Milne-Thomson method and I am following exactly the 4 steps. You can see the first step is let f of z is equal to u plus iv. Okay, b and analytic function with the real part. What is the real part? So these are the common notations of general notation. So it is going to be x square minus y square. Okay, so it is going to be the real part, and now we have to follow the next steps. Okay, so what is the next step? The next step is to find the first order derivatives, then name these derivatives, and then the next step will be put x is equal to z and y is equal to 0, and the last step is to integrate. Okay, so let us follow this. Okay, so what we have here, the next step we have consider. Okay, so it is real part, so phi of xy, that is w by x. Now we are finding the derivative of this term with respect to x only. So y is treated as a constant, so derivative of this term will be 0, and hence the derivative will be 2x only. The derivative of x square is going to be 2x. Next, we have to find out phi 2 of xy. So it is w by y, and hence the derivative of this term with respect to y. Now x is treated as a constant, so the derivative of x square is going to be 0, and the derivative of y square is 2y. So here you have, this is minus 2y, is equation 2. Okay, now the third step. What is the third step? Put x is equal to z and y is equal to 0 in equation 1 and 2. Okay, so we get, what do you have here? See the term, you will be having phi 1 of z0 is equal to 2z, and phi 2 of z0 is equal to 0, because we are putting y is equal to 0. So this is the third step, and now by the fourth step, what you will be having? By Milne-Thomson method. Okay, the analytic function of z, okay, is given as, so what is f of z? I'll suggest you always write the formula. Okay, so it is going to be phi 1 of z0 dz minus I integral phi 2 of z0 dz plus c. Okay, so we can see here what is phi 1. So phi 1 is integral of 2z dz minus I times this is 0 dz plus c. So what is the integration of 2? What is the integration of x? It is going to be x square by 2. So it is z square by 2. Okay, that's what you are here. And plus the integration of this is going to be 0 plus c. So 2 will get cancelled. It is going to be z square plus c. So what we have here, f of z is equal to z square plus c. Okay, so you can see this. This is going to be the function. Okay, so here we have, see the option. Okay, so which option is correct?
Option B, sir.
Option B is going to be correct.
B.
Okay, so this way in 4 steps you are able to get the answer. Okay, if this is theoretical question, then this explanation you have to write. Okay, if this is a MCQ question, then you have to choose this. Again, I will tell you the trick for getting the function. Okay, when the real part is given, this trick is applicable only if the real part is given. Okay, please remember that this trick is applicable only if the real part is given. Okay, so I'll show you the another example, and then we can see how the trick works. Okay, so here, if we consider that I have the similar type of problem, and then I want to find out the static function. Okay, so suppose real part is given, u is equal to x cube minus 3xy square is the real part. Okay, u is there, that means it's going to be a real part, and I want to find out the corresponding analytic function. Okay, and I don't want to do these calculations, or this is a MCQ, so I don't want to go through all these steps. X is equal to z and y is equal to 0. Okay, so if I do that, then what I'll be having here? So can you guess what this will be? Put x is equal to z and y is equal to 0. What will get here?
Z cube.
Z cube. So your analytic function is f of z is equal to z cube plus c. Now apply this trick for the previous example. So your u was x square minus y square. Okay, this was your u. Apply the trick. What it becomes? It becomes z square. This is going to be 0. And so see what is the f of z we have got. So f of z is z square plus c. But remember that this trick is applicable only for real part. Okay, for imaginary part it's different. Okay, or it's not that simple. Okay, but if you want to find for the real part, what will be your final answer? Okay, then simple. You put x is equal to z and y is equal to 0, and then whatever the term you will have, add the constant of integration. Yeah, so that will be your function f of z. Yeah. So now I want if you have any doubt or any query from your side, so please you can ask. So if you have any doubt or any query, you can ask. There is something in that box. No.
Yes, participants, you all may ask for any doubts or queries to sir.
These are the concepts that you need to practice. Okay, once you practice this concept, the MCQ and the theory will be easy for you.
You can also write your queries in the chat box.
हेलो सर.
Yeah.
यस सर, वो आपने जो रियल पार्ट्स के लिए जो ट्रिक बताया वो आप इमेजिनरी पार्ट्स के लिए वापस बता सकते हैं?
नहीं, imaginary part के लिए that is a little bit different. Okay, so for imaginary part you need to you cannot apply the same trick. Okay, simply that is applicable for real part. Yeah. Any other query, please?
हेलो
Yeah, Abhishek.
सर, एक कॉम्प्लेक्स वेरिएबल जो होते हैं ना,
Yes.
तो उनका रियल लाइफ एप्लीकेशन क्या होता है रियल वर्ल्ड में?
Oh, that's great. Again,
या
जैसा मैंने बताया कि every real thing is a complex. Yeah. So, for example, we know that there is a simple law of energy. What is the law of energy? Energy cannot be created nor be destroyed. Okay, only it gets transformed from one form to another form. Correct? Yeah.
यस.
The question is, all of us have studied the simple harmonic motion. Okay, so what happens in the simple harmonic motion? We give some energy to the mass, okay, and then let it go oscillate. Okay, but what happens at the end? It comes to rest. Correct? So at the end it comes to, why it comes to rest? Where the energy has gone. So there we do not consider the air resistance, okay, which is invisible and which is imaginary. So what happens is this energy is slowly consumed by this air resistance, which is complex. Okay, and if we consider the solution of this simple harmonic motion, okay, so what we have the solution of this simple harmonic motion, okay, so we can have, I hope you are able to see this, right?
Yes, sir.
Okay, so the equation of the simple harmonic motion is dx square by dt square plus k square x is equal to 0. Okay, so if you solve this, okay, what is the solution we'll have here? Okay, so the solution will be x is equal to, okay, here if I consider this k square, okay, so you'll be having a times sine of kt, okay, plus b times cos of kt. This is the general solution. Okay, so if we have this general solution, then we know this sine, what this sine is actually. So we know sine of theta is equal to e raised to I theta plus minus e raised to minus I theta. Yeah, this is going to be e raised to minus I theta by 2i, and this cos theta is nothing but e raised to I theta plus e raised to minus I theta by 2. And you can see, bingo, this is complex.
Okay.
Yeah, so that's how we started with the real life problem, simple harmonic motion, and we landed into complex. Okay, so this way, whenever there is a vibration, okay, whenever there is a wave, okay, these are all having their solutions in complex. Okay, they all land into complex domain. Okay, even though spring mass system or in electrical you go with the RLC circuits, okay, these all land into complex, and that's why we need to understand the complex. Okay, so if we go with the branch specific, there are application in each and every branch. Yeah, any other question please?
Thank you, sir.
Yeah, welcome.
रियल पार्ट का ट्रिक फिर से बताओ ना.
Real part ka tick. Okay, so what we have done in the real part, okay, see here you have, whenever you consider the function u is equal to x cube minus 3xy square, this is the real part of the function. Okay, and then we want to find the analytic function. What is the analytic function going to be? Okay, so what you have to do is simply put x is equal to z. Okay, so what we do here, we put x is equal to z and y is equal to 0. So if I put x is equal to z and y is equal to 0, then we are done. Okay, so what we do here, so if I consider put x is equal to z and y is equal to 0. So if you put x is equal to z and y is equal to 0, then you are able to get it. See here, this is the function u is equal to x cube minus 3xy square, and you put this is going to be z, so it will be z cube, y is 0, so this term is going to be 0, and then add the constant of integration, that is your function, which is analytic. So for example, here u is equal to x square minus y square, we have calculated it. Okay, but if you put x is equal to z and y is equal to 0, then this will be z square, and add the constant of integration c, that is going to be the function f of z, which is analytic. So is your query satisfied? Have you got it?
Yes, yes, okay, sir. Thank you.
Yeah, welcome. So any other question please?
Sir, how to decide real part or imaginary part? Means like little bit confusion है वहाँ पे, कैसा decide होता है real part and imaginary part?
Yes, very good. So the part which does not contain I is a real part, and the part which contain I is a imaginary part. Okay, so for example, we have solved one problem. Okay, what is the problem we have solved? Whether the function is analytic or not. Okay, so that problem we have seen here. Okay. See here, this is the question. So I hope you are able to see, right? Yeah. So
Yes,
here,
sir.
here what we did is we simplified. So here we have considered one part which does not contain I. Okay. So I have considered this part which is not having any term of I, and this is the part which having the term of I. So I have written here the part without I and the part with I. Okay. So the part without I is called real part, and the part without with I is called imaginary part. So here what will be having the real part u is x square minus y square, because we don't have I here. Okay, and the imaginary part b is equal to 2xy, because we have I associated with this part. So the part which does not contain I is a real part. The part which contains I is a imaginary part. So is that okay?
Yes, sir. Got it. Thank you.
Okay, welcome. So thank you, Inspire. Thank you, Kamlesh sir.
Thank you
very
so
much,
much,
sir,
sir.
for a nice session.
Thank you so much, sir, for rendering your precious time. I hope the participants had a lot to gain. Thank you, sir.
One thing just I want to add. Okay, so if you want more examples like this, please go to my YouTube channel. You will find all more examples on this complex and everything. Okay, so which will be sufficient for you for the preparation. Okay, so please visit the YouTube channel. That will be a resource for you. Okay, so you can just go there and have the topics which you want easily are available. Only thing is that the videos are lengthy, so you need to have patience. Okay, thank you. Yes, Inspre.
Thank you, sir. Thank you so much. On behalf of the entire Inspire team and Pillai HUC College of Engineering and Technology, I would like to thank you wholeheartedly. Thank you so much, sir.